doing multiple hypothesis testing. So we did a hypothesis test about a population proportion, and we're going to use, so we're going to do a hypothesis test about a mean, mu, right? A population mean, mu. And there are two things when we're doing a population mean, mu. Is sigma known or is sigma unknown? You're going to see sigma unknown more often, right, than when sigma is known, just based on the fact that it's a more type of realistic situation. But I'm going to show you both. She's up. I'll go to the calculator trick. I mean, these are the test statistics. This is for a test statistic. So notice when sigma is known, I use a z-score, and I have a population mean, a population standard deviation known. And this is the formula for a test statistic. When I'm testing a claim about a mean and sigma, the population standard deviation is unknown. Notice that I'm using S because I don't know sigma, and I'm using a t-score. So if sigma is unknown, then I'm going into student t-distribution. If sigma is known, then I'm going into z-scores and standard normal distribution. So let's look at this example. Z. When we did confidence intervals. So two situations, right? Two cases. If I'm doing a hypothesis test, this is only for a hypothesis test about a mean. This is not a hypothesis test about a proportion. This is a hypothesis test about a mean. What does a mean? A population mean, mu. I don't deal with this when I go into testing a claim about a P, a population proportion. So the two cases is whether sigma is known. And what is sigma? Sigma is the population standard deviation. Remember, we went through that way back in the beginning. I said you need to know the difference between S and sigma, and the difference between a sample and a population, and the difference between a statistic and a parameter, because later on it's going to determine your methods. If sigma is known, which is a population standard deviation, then I use Z's. My critical value is a Z-score. I'm on an SND curve. Or if I'm doing a hypothesis test, Z-test. If I'm doing a hypothesis or a critical confidence interval, Z-interval. That was from chapter 7. Right now we're doing tests. I might use intervals to run a test, but I'm going to run a test. If sigma is unknown, right, again, this is only considered if I'm doing a hypothesis test about a mean, mu. Then I have to ask this question. If sigma is unknown, then I'm using t-scores. My critical value is a student t-score, a t-score. I'm on the student t-distribution. This is the same idea as chapter 7. I'm using t-test or t-interval if I'm doing an interval. Right? If I want an interval of numbers, it ends in interval. If I'm running a test and I want a test statistic or a p-value, then I do t-test. So again, remember, with calculator tricks, in hypothesis testing, actually I'll write it over here. What does the actual t-test or z-test give you? What would you use? This is going to give the test statistic and the p-value. Same thing as the last section. One crop z-test gave the test statistic and the p-value when I did a claim about p. Now, I'm using z-test or t-test, dependent on the situation, and this is going to give the test statistic and the p-value. So I can use it for whatever the heck I want, whether I'm doing, I don't know, whatever method you're going to use, because there's 3 different methods that I could use. So I'm going to do this example. I'll find all the pieces. Remember, I'm going to show or talk about all 3 methods, 3 methods that I can use. I'll talk about the confidence interval method also in a second. But I'll start with the traditional method, or in your book, I think it calls it the critical value method, because I use the critical value. And then I'll do the p-value method. In a test of the effectiveness of garlic for lowering cholesterol, 49 subjects were treated with raw garlic. My subjects and sample size is 49. Cholesterol levels were measured before and after treatment. The changes before minus after. This is important later on. Are you doing before minus after? Are you doing after minus before? It's going to be important later on. But the changes The sample's changes have a mean of 0.4. A sample mean is x bar. And a standard deviation of 21. Is that a sample standard deviation or is that a population standard deviation? Does the standard deviation come from the sample of 49 subjects or does it come from the population in general treated with raw garlic? Well, here's the difference between the two scenarios. The changes before minus after in their levels of LDL cholesterol have a mean of 0.4 and a standard deviation of 21. And that implies coming from the sample. Versus if it sounded like this, the changes in their levels of LDL cholesterol have a mean of 0.4. The standard deviation of all levels is 21. What's the difference? All versus and, right? One of them comes from a population and one of them comes from a sample. You have to determine yourself which one it is based on the verbiage. You have to pull it from the problem. How do I determine? Well, this says and. So that means that this mean and this standard deviation come from this sample. If I said all, right, then that would imply population. This is something we practiced in chapter 1. So this is an S and not a sigma. S is 21. Right now it looks like sigma is unknown. Why do I need to know this? Well, that's going to tell me whether or not I'm using T versus E. So I probably need to know that. But let's see what I'm running a test about. Use a 0.05 significance level. 0.05 significance level. Alpha is 0.05. This is the same thing as the last section. Significance level is alpha. To test the claim that anytime I hear a claim, I go, here's my null and here's my alternative. I'm pulling these things from the problem. That with garlic treatment, now you guys have to determine whether it's a proportion or a mean. With garlic treatment, the mean change. This is a hypothesis test about a population mean. Mu. The mean change in cholesterol is greater than 0. So the null would be equal to 0. So this is a right-tailed test. Now remember, I told you guys that every time I do a word problem, I'm going to read it at least 3 times. Why? The first time is to determine what's going on. The second time is to pull the information from it. The third time is to verify the information that I pulled from it. And if you need to read it a 4th time, do that. That's just life. You got to actually interpret stuff. You got to read stuff and interpret it. In the test of effectiveness of garlic for lowering cholesterol, 49 subjects were treated with raw garlic. That looks good. Cholesterol levels were measured before and after the treatment. The changes in their levels have a mean of, so their changes, sample mean, and a standard deviation. Their sample standard deviation is 21. And then from wherever. Use a 0.05 significance level to test the claim, set this up, that the mean change, mu, is greater than 0. Alternative is greater than 0. The null always carries the equal to. So it's greater than, points to the right. The alternative tells us the type of test. It's a right-tailed test. So I'm going to practice finding the test statistic, finding the critical value, finding the p-value. These are all things that you could be asked for. Determining the conclusion based on those, and then interpreting that conclusion. Now, I'm running a test about a population mean. So based on the fact that I'm running a test about a population mean, I have to ask the question whether sigma is known or sigma is unknown. This is the same process as in chapter 7. Is sigma known or sigma unknown? Well, I saw nothing about a population standard deviation, so sigma is unknown, and therefore I use T. T-test, T-interval, student T-distribution, whatever the heck you guys, need, basically. Whatever you need. T-test if I want, right? T-test if I want a test statistic or a p-value. T-interval if I want an interval, right? How do I find my critical value? Where do I find that? I'm not going to use inverse norm. Let's go critical value right now. Critical value corresponds to a rejection region / critical region. And if it's a right-tailed test, that critical region / rejection region is in the right tail. The area of the rejection region is alpha. This is the same thing as in the last section. This part did not change. The critical value is the value separating this rejection region from the rest of the curve. What is this curve? It's a student t-distribution curve. How do I know? Sigma is unknown, and I'm testing a claim about a mean. My critical value is a t-score. Okay, now how did I find a t-score if I know an area? Well, we remember, like, how do I find a z-score if I know an area? Well, what did I do? I went and I used inverse norm. But when we did this in chapter 7, and we used the student t-distribution, we had to go and use, where's my table? We had to go and use table A3. I had to use this table to determine the critical value because not everybody had inverse t. Some of you did, so some of you used that, but not everybody had that. So, unfortunately, I don't know why it's a little kind of zoom in a little bit. So, remember this table, we're using it again. The body of this table, right, is your t-score. This table requires degrees of freedom, and it requires an area in one tail or an area in two tails. Well, what do I have? I have the area in the right tail, which is an area in one tail, as 0.05. So my area in one tail is 0.05. How do I determine degrees of freedom? Well, degrees of freedom are based on sample size, and our sample size is 49. And degrees of freedom is always one less than sample size. So our degrees of freedom are 48. Back to my table. I go down. 48 is not on my table, so what did I say to do? If it's not here, you have to round to the closest. So we'll go to 50, right? So I'm going to 50 degrees of freedom, which is down here at this row. And then what did I say? The area in one tail was 0.05, so that's the second column from the right. So I'm going to line it up. 50 degrees of freedom. Second column, 1.676 is my critical value for this situation. 1.676. So let me go back to my curve, and the critical value here is 1.676. Now I'm going into details, right, because of the fact that I'm going through everything, right? So most of the time I don't even write this down. I can go straight to the table, find my value. But now I have my critical value, which is a student t-distribution, which is approximately 1.676, and it's positive because it's in the right tail. Let's go to my test statistic. Yeah, you can use inverse t if you have it. Sometimes it's faster to do the table actually if it's t-scores. It's going to be a little off if you use your calculator versus if you use the table, because we had to approximate with the table and round to the closest degree of freedom. So the calculator would be more accurate, but you should be okay regardless of which you use. All right, so where do I find my test statistic and my p-value? So I'm going to go to t-test, right? T-test. Why t-test? Because sigma is unknown, and I'm doing a hypothesis test about a mean. Where do I find t-test? I am living in stat and tests for all of chapter 8, 9, and 10. All hypothesis testing, all confidence interval, all that stuff. I'm going to stat, and I'm scrolling over to tests. It's all here. Remember I told you when we did confidence intervals, though, you don't want to confuse the stuff that ends in tests with the stuff that ends in interval, right? But it tells you exactly what it is. Int is interval, test is test. I'm going to go up to t-test. Enter. Because I want a p-value and a test statistic. This is similar to chapter 7, where do I determine or do I use data or do I use stats? I don't have a list of numbers, right? See, this is asking for a list of numbers. I don't have that. So I'm going to scroll over to stats because I have statistics. I have X bar. I have statistics. I have values. Now, mu naught is the value that's on the null hypothesis, which in this case, the claim or the null hypothesis says that it's equal to 0. So mu naught is 0, okay? X bar, let's go back to my stuff. X bar was 0.4, and then Sx is the sample standard deviation. Notice that if I'm in T, it asks for S. If I were in Z, it would ask for sigma. It tells you. Sx was 21. That was a pretty large standard deviation, actually. And then N was 49. And then I have to tell it which type of test, which we said was right-tailed. So I want that to be highlighted. Enter to keep it on that. And then let's go down to calculate. Same process, same order. Alternative hypothesis first. Test statistic second. P-value third. And then this tells me sample mean, sample standard deviation, and sample size, which I could verify and compare to what I had written down. Or if I didn't have it, it would give me that too. But same thing, alternative, test statistic, p-value. Notice the test statistic is a t-score. Well, I'm on a t-test. Why am I on a t-test? Sigmas are known. This is the same thing as chapter 7. Go back to, back to my whatever. My test statistic was t-scores were usually around to 3 digits to the right, so 0.1333 for my t-score. So the test statistic is approximately t equal to 0.1333. My p-value, right, is underneath that. P-value is a large p-value, 0.4472. And the p-value is an area, so we're going to take more digits, 0.4472. And now I can actually do whatever the heck method I want to run this test. I'm going to discuss all 3 methods for this one. The first method, traditional method. I want to know where the test statistic is in comparison to my critical value and my rejection region. My test statistic is 0.133. That is closer to, remember, the center of this curve is 0. 0.133 is less than 1.676. So it's over here somewhere, right? Because this is a number line, technically. It goes from least to greatest. So the test statistic doesn't make it past the critical value, which means it's not over here in this rejection region area, which means the test statistic is not there. I cannot reject it. I fail to reject the null. According to the traditional method, the test statistic is not in the rejection region, so I cannot reject, so I fail to reject the null. Right? My conclusions, either rejected or fail to reject, same thing. My other method that I can use, the p-value method, is comparing the p-value to your alpha. Well, the p-value is 0.44 and alpha is 0.05. And 0.44 is bigger than 0.05. And when the p-value is bigger than the alpha, the significance level, we fail to reject the null. From the p-value method, the p-value has to be smaller than alpha for you to reject. If it's not, then you can't reject. So I fail to reject the null. Interpretation, right? I'll do my confidence interval method in a second. Now I determined that I'm going to fail to reject the null. Now what does that mean for my situation, right? You can go back to the problem. I go back to the word problems to look at what the heck I need. But at the same time, it's really here, looking at the alternative and the null, and then here. So if I am failing to reject the null, then there is insufficient evidence to support. I'm failing to reject the null. I'm not rejecting the null. So I'm going to support the alternative, which says the mean is bigger than 0, which matches the words here. There is sufficient evidence to support the claim that with garlic treatment, I'm copying this straight from here. With garlic treatment, the mean change in LDL cholesterol is greater than 0. Come to the conclusion, regardless of what method you use, to fail to reject. Failing to reject. I can't reject this. So there's insufficient evidence to support this. The only funky wording is when a two-tailed test happens, but this is a right-tailed test, this is a one-tailed test, not crazy. When you are rejecting the null, then there's sufficient evidence to support the alternative, right? When you're rejecting the null, throwing the null away, this is gone, then I'm supporting this. There is sufficient evidence to support this, and you have to convert this into words. So you have to know what the variables mean relative to your situation. Go back and forth between words and notation, math terms and verbiage. If I fail to reject this, I cannot reject this, I cannot throw it away, then there is insufficient, right, evidence to support whatever this says. There is insufficient evidence to support the claim that with garlic treatment, the mean change in LDL cholesterol is greater than 0. And you want to be detailed like that, because at the end of the day, you are testing this claim. Hypothesis testing is used a lot. And I know I have a lot of medical people here because statistics, a lot of medical people have to take statistics. You see a lot of hypothesis testing in the medical field. So,